Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing single-phase semi-converter. We can also call it as a half-bridge converter with R load. If you see this half-bridge converter, it consists of two thyristors and two diodes. That means half of the devices are controllable devices and remaining half, that is diodes, are uncontrollable devices. And if you see, converter basically converts AC to DC supply. And here in a half controlled converter, it converts both positive half cycle as well as negative half cycle of the output voltage. And even if you see, full converters also serves the same purpose. Then why are we affording for two more thyristors over there? It is because full converters can be applicable for higher rating applications, whereas when compared to that of half bridge converters, that is the only difference. And the one more difference is full converter provide two quadrant of operation, whereas half bridge converter, it facilitates only one quadrant of operation, where output voltage is positive as well as output current is positive. It only provides one quadrant of operation. That is the basic difference between a half bridge converter and a fully controlled converter. Coming to the detailed operation of a half bridge converter, see, during the positive half cycle, that is during the positive half cycle of the supply voltage, what happens? The polarities will be here positive, negative, and since anode of the thyristor 1 is more positive with respect to cathode, T1 is forward biased. At the same time, since diode is more negative, diode 1 cathode is more negative with respect to cathode, even D1 is forward biased. That means T1 as well as D1 both are ready to conduct. That is, it is in forward blocking state, not at conducting state. And once during the positive half cycle, if we can provide the triggering pulse for thyristor 1, in that case, thyristor starts conducting a current through the load. So, during the positive half cycle, let me draw the individual circuit diagram. It looks like this. During the positive half cycle, since T1, the moment when we provided the triggering pulse, T1 started conducting current through the load, through D1, So, this is how current started conducting through the load. That is, supply voltage, thyristor 1 got short circuited the moment when we provided the triggering pulse, and it is driving the current through the load through D1 and back to supply. This is what the current direction through the load. And when the current is flowing through the load, what are the supply voltage which we are actually feeding is applied across the load. So here V0 is equal to Vs, and that is how the moment when we provided the triggering pulse, here thyristor 1 as well as diode 1 started conduction, and it is conducting right from alpha to pi. So here T1 as well as D1 is conducting. So that is the reason whatever the supply voltage which we are feeding is applied across the load. So what? Your output voltage right from alpha to pi. Your output voltage right from alpha to pi is just similar to that of the supply voltage. It is following the supply voltage waveform, and that is how we are getting the output voltage right from alpha to pi when T1 and D1 is conducting. And the moment it reaches pi, what happens? Negative half cycle has been appeared, and because of the supply terminals, supply voltage, the polarities across this particular devices will be now negative, positive. And if you see, because of these polarities, anode of the thyristor 2 is more positive with respect to cathode. So T2 has come into the forward blocking state, and at the same time D2 negative, that is D2 cathode is more negative with respect to anode, so D2 is also forward biased. So that is the reason during the negative half cycle, that is from pi plus alpha, the moment when we provide the triggering pulse, thyristor 2 and diode 2 conducts from pi plus alpha to 2 pi. So if you see the individual circuit diagram, this is during the positive half cycle, and during negative half cycle, let me draw the individual circuit diagram. See, it looks like this. Thyristor 2 started conduction and it is conducting current through the load. In this direction, I0 is flowing, and again D2. So this is how the current is flowing through the load. That is, the path is like this. T2 is short circuited. It is conducting current through the load and back to D2 and back to supply. This is how current is flowing through the load in the negative half cycle. And if you see, whatever the supply voltage is actually applied across the load, even during the positive half cycle, current through the load is in this direction, that is downwards. Say from A to B, current is flowing, output current is flowing. Even during the negative half cycle, current through the load is flowing in the same direction, that is from A to B. And that is how whatever the supply voltage which we are feeding will be applied across the load. So here V0 is equal to Vs, and that is the reason from pi plus alpha to 2 pi, whatever the supply which we are actually feeding is applied across the load. That is the reason it is following the waveform of the supply voltage. So that is from T2 and D2. T2 and D2 is actually conducting from pi plus alpha to 2 pi because of the negative half cycle supply polarities. And again, during the positive half cycle, the cycle repeats. That is, from 2 pi plus alpha to 3 pi, T1, D1 conducts current through the load. And that is how we are getting the output voltage through the load. And this is the output voltage waveform which we have seen. And coming to the output current, it is just similar to that of the output voltage, because output current is equal to V0 by R. So only a magnitude will be differed by a little, but the waveform will be one and the same. So right from alpha to pi, current is flowing through the load, and this is due to T1 D1. And again, from pi plus alpha to 2 pi, current is flowing through the load, and this is due to T2 D2. This is nothing but the output current waveform. And now let us see the individual current which is flowing through thyristor 1 as well as diode D1. And if you see, that is from alpha to pi, thyristor 1 as well as diode 1 is conducting. So that is the reason this is the waveform which of the current which is flowing through thyristor 1 as well as diode 1, and it is present from alpha to pi, since from alpha to pi thyristor 1 as well as diode 1 is conducting. This is the current through the thyristor 1 and D1, that is IT1 and ID1. And again, current will be flowing through the thyristor 1 and D1, that is from instant 2 pi plus alpha to 3 pi. Why is it so? Again, during the positive half cycle, thyristor 1 and D1 comes into the picture. It starts conducting, and that is how current starts flowing through the device, that is IT1 as well as ID1. And if you see, let us also check the current waveform, that is current flowing through thyristor 2 as well as diode 2, and that is from the instant pi plus alpha to 2 pi, thyristor 2 as well as D2 are conducting, that is during the negative half cycle. The current is flowing through thyristor 2 as well as diode 2. Coming to the supply current waveform, if you see supply current waveform during the positive half cycle, let us check. See, during the positive half cycle, since current is flowing downwards, D1, and back to supply, during which the current flow through the supply is upwards direction. Upwards direction, say this is from P to Q. From P to Q, the supply current is flowing in the upwards direction, and that is the reason from alpha to pi, when the current is flowing through the load, the devices so-called T1 as well as D1 is drawing the current through the load, and that is how we get the supply current from alpha to pi, that is from alpha to pi, and this is due to the T1 and D1 is drawing the current through the supply, and this is flowing in the positive direction. That is how your supply current waveform. Supply current waveform is positive. Similarly, we will check the supply current waveform during the negative half cycle. That is, during the negative half cycle, what happens? Thyristor 2 as well as diode 2 comes into the picture, and that is the reason from pi plus alpha to 2 pi. If you see, let us check out the current path during the negative half cycle. See, during the negative half cycle, current is flowing through T2, load, D2, and back to supply, and now current through the supply is flowing in the downwards direction, that is opposite to that of the first case. During the positive half cycle, current is flowing from P to Q, whereas here the current is flowing from Q to P, reverse to that of the first case. So that is the only reason supply current waveform during the negative half cycle, it is from pi plus alpha to 2 pi is negative. Supply current is negative. Whereas output current in both the cases is flowing in the same direction. That is from A to B, A to B, and even during the negative half cycle, supply current is flowing from A to B. That is the reason converter converts output voltage, it converts AC to DC, and that is how we are getting the output DC voltage. Whereas input voltage is AC. It has got both positive half cycle as well as negative half cycle. Hope you understood this concept. Coming to the average output voltage, if you see V0 average, the general formula we have is V0 is equal to 1 by T conducting from 0 to T, V0 of omega T d omega T, where here the total time period is, if you see the time period, every similar cycle is repeating for pi. So that is the reason here I am taking time period as pi, and it is actually conducting from alpha to pi, where V0 is Vm sine of omega T d omega T, constant bringing it out, Vm by pi minus cos omega T d omega T, conducting from alpha to pi, these are nothing but the limits, alpha to pi, and substituting the limits, upper limit minus lower limit, minus cos pi, minus of minus plus cos alpha, and here cos pi value is minus 1, minus of minus plus 1, 1 plus cos alpha. This is nothing but V0 average expression. And here V0 RM is, where V0 RM is, the general formula which we have is 1 by T 0 to T V0 square of omega T d omega T whole to the power of 1 by 2, where here the time period is 1 by pi conducting from alpha to pi. V0 is equal to Vm square sine square omega T d omega T whole to the power of 1 by 2, and here Vm square bringing it out, Vm square by pi, and in order to integrate sine square, I am writing this in terms of cos 1 minus cos 2 omega T by 2 alpha to pi, and here Vm square by bringing the denominator out by 2 pi, integration of 1 is omega T conducting from alpha to pi, minus integration of cos is sine 2 omega T by 2 alpha to pi, and here I'm applying whole to the power of 1 by 2 to this expression. We get Vm by root 2 pi. Substituting the limits, pi minus alpha minus upper limit minus lower limit, that is sine 2 pi by 2 minus of minus plus sine 2 alpha by 2 whole to the power of 1 by 2, which is equal to Vm by root 2 pi minus alpha minus, this is 0. So this whole term sine 2 pi is 0. That is the reason whole term is 0. Plus sine 2 alpha by 2 whole to the power of 1 by 2. This is nothing but your V0 RMS expression for single phase semi-converter with R load. And in the coming lecture, we will be seeing single phase semi-converter with R load.